Dr. Seyadali Fatima, Assistant Professor, Department of Mathematics, Majigatra College, Uttamapalayam. Dear students, today we are going to discuss about set theory. In set theory, we see definition of sets, set notations, types of sets, and operations on set. A set is a collection of well-defined objects. Sets are usually denoted by capital letters A, B, C, and their elements are denoted by small letters A, B, C, etc. We see some examples in set. The collection of vowels in English alphabet is a set. The set of 3 cycle companions of India. The set contains 3 elements: hero, avan, and sun cross. The set of 4 rivers in India. This set contains 4 elements: Ganga, Yamuna, Narmada, and Kaveri. Now we see the representation of set, this rostered form and builder form. In rostered form, this method is also called tabular method. In this, a set is described by listing elements separated by commas within braces bracket. The collection of vowels in English alphabet, the set contains 5 elements, that is set of all A, E, I, O, U. If capital A is the set of even natural numbers, then A contains the elements set of all 2, 4, 6, etc. The order of writing the elements of a set is immaterial. An element of a set is not written more than once. In builder form, this form is also called property form. In this, a set is represented by starting all the properties P of X, which are satisfied by the elements X of the set and not by other element outside the set. We see some examples. If capital A is the set of even natural numbers, then A can be written as A equal to the element X such that X belongs to capital N. Here N is a natural numbers and X is equal to 2N. Next we see some types of set. In empty set, a set is used to a set is said to be empty or null or void set if it has no element and is denoted by pi. In rostered method, it is denoted by flower bracket, open and closed bracket. Here see the example. The set A, which contains the elements X such that X is greater than 7 and less than 8 is equal to pi. And another example, that B equal to the element X belongs to R such that X square is equal to -2, which is an empty set. Pi is not a null set since it contains pi as an element. The brace 0 is not a null set since it contains the element 0. Next we see singleton set. A set is said to be singleton set as it contains only one element. It's an example for singleton set 5. 0 is the example for singleton set. Next we see the finite set. A set whose elements can be listed or counted. Here the example A equal to set of all 1, 2, 3 and 5, 10, 15, 20 are finite sets. Infinite set, a set whose elements cannot be listed or counted. The set of all real numbers is an infinite set. Equivalent sets. Two finite sets capital A and capital B are equivalent if their cardinality numbers are same. That is n of A equal to n of B. Here the example A contains 5 elements and the set B contains 5 elements are equivalent. Equivalent sets. Two sets A and B are said to be equal if every element of A is the member of B and every element of B is a member of capital A. The example, if A is the set of even natural numbers and B equal to 2, 4, 6, etc. Here the set A and B are equal, which contains set of all natural numbers. Let's see subset. If in two sets A and B, if every element of A is an element of B, then A is called a subset of B. If A is a subset of B, we write a subset of B. Thus, a subset of B if A belongs to A, which implies A belongs to B. If A is a subset of B, then B is called a superset of capital A. Next, we see some properties of subsets. The null set is a subset of every set. Every set is a subset of every set. If A subset of B and B subset of C, then A subset of C. The total number of subset of a finite set containing n elements is 2 power n. In proper subset, a set is said to be proper subset of B if A is a subset of B, but A is not equal to capital B. It is denoted by A contain B. In example, the natural numbers n contain whole numbers. Whole number contains z set of integers. Z contains q and q contains real numbers. In universal set, it is a set which contains all the sets under consideration. That is, it is a superset of each of the given sets is denoted by capital U. Set of a real number is a universal set. In power set, the collection of all subset of n given a set is called a power set. It is denoted by P of A. Next, we see some operations on set. A union of B is the set of all elements that are in A or B or both. This is similar to the logical OR operator. The intersection A's intersection B is the set of all elements that are in both A and B. This is similar to the logical AND. Next, we see set complement. A complement or not A is the set of all elements not in A. The complement operator is similar to the logical NOT and reflexive is that A power double bar is equal to capital A. Here we see some examples of A union B and A intersection B, A bar and B bar. Venn diagram. Venn diagrams use topological areas to stand for sets. This is A intersection B. We say that a group of set is exclusive of another set if their union is equal to the set. For example, we say that A and B are exhaustive with respect to the set capital C. Therefore, A union B equal to C. We say that two sets A and B are mutually exclusive if A intersection B is equal to pi. That is, the set have no element in common. This diagram represents A union B, A intersection B, and A minus B, B minus A. Symmetric difference of two sets are that is denoted by A delta B. A delta B is equal to A minus B union B minus A. some properties of complement. U dash is equal to pi and pi dash equal to u. A dash the whole dash is equal to A union A dash is equal to u, and A intersection A dash is equal to pi. If A subset of B, then B the subset of A dash. So example for here, the example A, B union. Now verified that A minus B is equal to A dash and B dash is equal to B dash minus A dash. Now we see the fundamentals law of algebra of sets. First one, the idempotent law. A union A is equal to A and A intersection A is equal to A. Next, identity law. A union pi equal to A and A intersection U is equal to capital A. It's commutative law. A union B equal to B union A and A intersection B is equal to B intersection A. Next, you see associative law. A union B union C equal to A union B union C. It's distributive law. A union B intersection C is equal to A union B intersection A union C, and A intersection B union C equal to A intersection B union A intersection C. Now see De Morgan's law for A and B. A union B the whole dash is equal to A dash intersection B dash, and A intersection B the whole dash is equal to A dash union B dash. Now applications of sets are n of A union B equal to n of A plus n of B if A intersection B is equal to pi, n of A union B equal to n of A plus n of B minus A minus n of A intersection B if A intersection B is not equal to pi, and n of A union B equal to n of A minus B plus n of B minus A plus n of A intersection B, and n of A union B union C is equal to n of A plus n of B plus n of C minus n of A intersection B, B intersection C, and C intersection A plus n of A intersection B intersection C. The n of A equal to n of A minus B plus n of A intersection B, and n of B equal to B minus A plus n of A intersection B. Thank you, students.